All right, kiddos, welcome back. We're continuing our discussion on pH and pOH. In the last video related to this, we solved for the pH by using this equation. pH equals the negative log of the hydrogen ion concentration. We also solved for the pOH by using this equation. pOH equals the negative log of the hydroxide concentration. And remember, the sum of pH and pOH is always equal to 14. So if we know one or the other, it's pretty easy to find the one that's missing. Well, today we're going to do things a little bit backwards. This time I'm going to give you the pH, and I'm going to ask you to find the hydrogen ion and hydroxide concentration. To do that, we're going to use this equation. The hydrogen ion concentration is equal to 10 to the negative pH, and the hydroxide ion concentration is equal to 10 to the negative pOH. Pretty straightforward. We shouldn't have much difficulty with this. So, if milk has a pH of 6.5, let's find the hydrogen ion concentration. So we're going to go 10 to the negative 6.50. So we're going to use our calculator. We'll plug in 10, then we'll hit our caret key, and then the negative button, 6.50. And we end up with 3.2 times 10 to the negative 7th moles per liter. Now for the hydroxide concentration, we can do that a couple of different ways. We can take Kw and divide it by the hydrogen ion concentration to get the hydroxide ion concentration, but I prefer to do it this way. I'm going to go 10 to the negative 7.50. Now you might say, where did you get 7.50 from, Hummer? Well, remember, the sum of pH and pOH is 14. If my pH is 6.5, my pOH is 7.5. So the hydroxide concentration would be 10 to the negative 7.50. So 10 caret key negative 7.50 gives me 3.2 times 10 to the negative 8th moles per liter of hydroxide ions. Now just for the record, if you multiply the hydrogen ion concentration times the hydroxide ion concentration, you should get Kw, which is 1 times 10 to the negative 14th. All right, why don't you pause the video and do the next 3, then come back to the video. We'll see how you did. All right, welcome back. So lemon juice has a pH of 2.37. Well, we know that's pretty acidic, don't we? So let's figure out the hydrogen ion concentration. That's 10 to the negative 2.37. So 10 caret key negative 2.37. Did you guys get 0.0043 moles per liter, or 4.3 times 10 to the negative 3rd? The hydroxide concentration, well, let's see. We have 14 minus the pH, 2.37, gives me the pOH of 11.63. So we're going to go 10 to the negative 11.63 for the hydroxide ion concentration. So 10 caret key negative 11.63 gives me a hydroxide ion concentration of 2.3 times 10 to the negative 12 moles per liter. Milk of magnesia, we use that to help cure an upset stomach. It has a pH of 10.5, so it's basic. The hydrogen ion concentration would be equal to 10 to the negative 10.50. So 10 caret key negative 10.5. And we end up with 3.2 times 10 to the negative 11th moles per liter. The hydroxide concentration would be, well, let's see, if we take 14 minus 10.5, gives us the pOH of 3.5, so it'd be 10 to the negative 3.50. So 10 caret key negative 3.50 gives me 3.2 times 10 to the negative 4th moles per liter. And then finally ammonia, of course we know that's basic, has a pH close to 12, 11.90, So the hydrogen ion concentration is 10 to the negative 11.90. So 10 caret negative 11.90 gives me 1.26 times 10 to the negative 12th moles per liter. And my hydroxide concentration would be 10, let's see, 14 minus 11.9 to the negative 2.1. And so let's see what that equals. 10 caret negative 2.10 is 0.0079 moles per liter. Okay? Alrighty, so on our next assignment we'll be doing several of these types of problems. You can go back and review the last couple of videos on pH and pOH and how to find the hydrogen ion and hydroxide ion concentration from those values. All right, let's do another weak acid problem here. Let's work with a 0.5 molar solution of acetic acid. The Ka for this is 1.8 times 10 to the negative 5th. Remember, equilibrium and an equilibrium constant. Let's write the reaction that occurs here. HC2H3O2 AQ plus H2O liquid reacts to form H3O positive AQ, and we'd end up with C2H3O2 negative AQ. Now recall we like to clean this up just a little bit, so if I get rid of water from both sides of the equation, so let's do that. We're going to get rid of water here and the H2O part of this, and then we'll rewrite the equation as HC2H3O2 AQ forms just H pluses AQ and C2H3O2 negatives. All right. Now, initially, the concentration of my acetic acid is 0.500 molar. That was given right here, kiddos. And we don't have any H pluses or acetate ions to begin with. And recall that this is a weak acid, so this goes down by a certain amount. We don't know how much yet. And whatever that goes down by, the hydrogen ion concentration goes up by that same amount, and so does the acetate concentration. So at equilibrium, we have 0.500 minus X, X, and X for our three species. So let's write the equilibrium expression for this. Ka equals, remember we put products over reactants. It's been a little while since we've done this, hasn't it? H plus times C2H3O2 minus all over HC2H3O2. Alrighty? Now we can plug in some numbers here. My Ka was given 1.8 times 10 to the negative 5th, and that will equal the hydrogen ion concentration at equilibrium, which we know is X, times the acetate ion concentration, which we know is X, all over the acetic acid concentration, which is 0.500 minus X. Right there, kiddos. So now this just becomes a simple math problem. We need to solve for X. Now we're going to make this a little bit easier. If my equilibrium constant is 10 to the negative 4th or smaller, and this is 10 to the negative 5th, folks, this X that we're adding or subtracting becomes negligible. It's so small, when I subtract it from 0.500, I still end up with essentially 0.500. So we're going to neglect that X and make this equation look just a bit prettier. Now it's 1.8 times 10 to the negative 5th equals X squared on top over 0.500 on the bottom. So we're going to multiply both sides by 0.5. So 1.8 second EE negative 5 times 0.5. And then we're going to take the square root of that answer to solve for X. And so X equals, and this will be the hydrogen ion concentration, and I get 0.0030 moles per liter. Okay, once again, I just multiplied both sides by 0.5 and took the square root of that answer to solve for x, which we know is my hydrogen ion concentration, and that's one of the things I wanted to solve for in my problem. Well, now I can solve for the pH, can't I? The pH is the negative log of that number. So we're going to take the negative log of that answer, and I get 2.5. So now we have the pH of that solution. Well, the pOH of that solution shouldn't be that bad. The pOH would be 14 minus 2.5. And so we end up with 11.5 for the pOH. So we now have the pOH for that solution. And then finally, the hydroxide concentration should be pretty easy to find. Wouldn't that be 10 to the negative pOH, which is 10 to the negative 11.5. So 10 caret key negative 11.5, and we end up with 3.2 times 10 to the negative 12th moles per liter. Alrighty, so that's about as hard as it gets, kiddos. A weak acid equilibrium problem, and we do those lots more in AP Chemistry next year. For this year, I really just want to show it to you. Alright? Let's do another one just for fun. Why don't you try example 8, see if you can handle it. This is benzoic acid. It's HC6H5CO2. And when that ionizes, it forms H pluses and C6H5CO2 negatives. Now this is initially a 0.100 molar solution. So pause the video and see if you can finish off this problem. Solve for the H plus, the pH, the pOH, and the hydroxide ion concentration. Then come back and see how you did. Alrighty, welcome back. Just like the last problem, folks, initially you didn't have any hydrogen ions or benzoate ions. The change in concentration, since this is a weak acid, we don't know how much this goes down by. If it were strong, all of it would ionize, but since it's weak, we don't know. So we're going to say it's going to go down by X, and it's a 1-to-1 ratio, so my H plus will go up by X, and my benzoate ion will go up by X as well. So at equilibrium, we will have 0.100 minus X, X, and X. Now we can write the equilibrium expression. That's products over reactants, kiddos. H plus times C6H5CO2 negative all over H C6H5CO2. And let's plug in some numbers. My Ka for this, ooh good, it's 6.5 times 10 to the negative 5th. That's really, really small. And that will equal my H plus, which is X, times my benzoate, which is X, right? X and X, all over my benzoic acid, which is 0.100 minus X. Right up there, kiddos. Now, since this is 10 to the negative 4th or smaller, in this case it's 10 to the negative 5th, we can neglect adding or subtracting X, because it's so small it won't affect that concentration. That's going to make the math lots easier. So we can rewrite this as 6.5 times 10 to the negative 5th equals X times X is X squared on top, all over 0.100. So now we can solve for X. We'll multiply both sides by 0.1 and take the square root of that answer. So X will equal the hydrogen ion concentration, which is, let's see, 6.5 second EE negative 5th times 0.1. Of course, that's 6.5 times 10 to the negative 6th. We're going to square root that so we can solve for X. So I press my second square root key and then second answer. And I get 0.0025 moles per liter. Now the pH is pretty simple. That's the negative log of that. So let's see what that turns out to be. 2.6. And the pOH is pretty simple now. Wouldn't that be 14 minus the pH, which gives me 11.4. And then finally, we can solve for the hydroxide ion concentration, which is going to be 10 to the negative pOH, which is 10 to the negative 11.4 here. So 10 caret key negative 11.4. We end up with 4.0 times 10 to the negative 12th moles per liter of hydroxide ions. So, how did you do on that problem? If you did well, congratulations. Like I said, we're not going to worry about that too much this year, but I wanted to introduce it to you, especially for those kiddos that are taking AP next year. We do this a lot. All right, hope you enjoyed today's lesson. We'll see you soon. Bye-bye.